Okay. How y'all? How's everybody doing? Pretty good? Fantastic. Okay, well, it's nice to see everybody. Welcome to our latest lecture of whatever this class number is, 68410. It's nice to see you all. Thank you to those of you who came on time today. I thought I'd surprise you by actually starting at the right minute. Let's see, in terms of announcements and things, your homework 2 was due yesterday, I think. Yeah, none of you guys had any substantial questions about it. I was ours, so I'll make the next one harder. That's duly noted. And your project proposals as well. So my goal is in the coming week and a half to give you feedback on all of your project proposals. Feel free to nag me to do that because I tend to procrastinate on tasks like that because they're boring. Similarly, I will post homework 3 by tomorrow. I wanted to spend an extra minute actually going through it because last time it was too hard and it got people unhappy. So I thought I'd maybe remove a problem or two before sending it out again. Or maybe not. It can just make you suffer. I don't know. We'll decide. In any event, so that's homework 3. The next little part of your project is going to be this check-in. Remember, essentially, what we're looking for in the project check-in is like signs of intelligence, right? You know, we want to see some evidence that you started. that's what we're looking for. Essentially, I noticed that even in this PhD level course, if I don't give you guys structure to your course project, you don't start it till the day before. So at least you have 3 or 4 days where you have to make some epsilon amount of progress before the final deadline. Okay. Any questions about that? No? Interesting recipes, favorite colors, top secret, MIT, cool places to go. Yeah, you guys kill me. Okay, so let's see. In our previous lecture, we talked about a little bit of the theory of geodesic distances, and in particular, we derived the usual formula using a very extrinsic argument, right? We use a lot of projections onto tangent planes and things to show that a geodesic curve on a surface has this property that it has 0 geodesic curvature, right? And do we remember what that means, either intuitively or mathematically? Anybody want to give us a reminder? Bueller? Yeah. Yes, Kartik, thank you. That's right. If I'm driving a car along my surface, I'm essentially not turning the steering wheel, right? Or to put it differently, if I look at the acceleration of a curve as I draw along the surface and parametrized by arc length, then the acceleration is parallel to the normal. It has no component in the tangent plane, right? And we wrote down this ODE that differential geometers know and love. It's their deepest secret. If you take the projection onto the tangent plane at the curve location of your surface of the second derivative with respect to arc length, this thing is identically 0. Yeah? Remember this triple equal sign? Somebody was asking me the other day. You can read that out loud as is identically is how we're using it in this class. Okay? So as usual in 68410, we ping pong back and forth between smooth and discrete. We worked through some coarse version of the smooth theory last time of geodesics. And again, remember, we're doing a very compressed version of differential geometry. I mean, if you took a class in the math department, you spend quite some time analyzing these formulas and not doing some sloppy arguments that we did. But instead, in this class, now that we have some idea of what does it mean to be a geodesic? What does it mean to be a local geodesic versus a global one, and so on, we're going to examine exactly those same questions, but now on a polyhedral object, right? That's our pattern. We kind of ping pong back and forth. And so essentially, we can ask exactly the same kind of things, what does it mean to be a geodesic curve? Is there a condition for local optimality? How does it differ from global optimality? And kind of compare it to the smooth case. And I think it's sort of unsurprising what we're going to do today. That sound good? Oh, you're nodding. Good, you guys are starting to wake up. That's fantastic. So if you remember from our last lecture, I kind of hinted that there are all these different geodesic distance problems one might consider on a surface, right? And they all feel related, and that's because they are. but they're not quite the same, right? For instance, you could look for a locally shortest path. If I tie a string around my surface and I start pulling it tight, what is the curve that I'll eventually get if I do kind of gradient descent on length? Remember, we talked about last time, unlike in Euclidean space, there are local optima here, right? So this weird double torus with an earth texture on it is a great example where, for example, that green curve is kind of knotted around the handle, and you can pull it as tight as you want, and it'll never get as short as the red one, right? So local and global optima are not the same anymore. But there are other queries that are somehow not quite the same, right? So for instance, on the upper right here, we're mentioning one source point to all target point distance query, right? So in other words, I want a function on my domain that says at every point on that surface, what is the shortest path distance globally to the source point? That's what we're going to spend most of our time on today. And then there are other ones, like multi-source shortest path, like if you wanted to do some kind of Voronoi diagram, or even all pairs shortest path, which is a pretty tricky problem. Okay? So we're going to mainly focus on these top two today, because I think those are the most common ones that you encounter in applications, and also because those are the ones I know about. Okay, folks. So we're going to start by talking about geodesic paths. So namely, like if I have a point on a triangulated surface, or really any surface with the kind of planar faces, the question is how much of our smooth theory, like how much of this formula here really applies anymore, right? And what we're going to see is it's a really subtle picture, which is kind of surprising and interesting and fascinating and cool. Like, and the reason why this is so interesting, I think, I really like this stuff. Like in our past couple lectures, we've often had to take notions like curvature and then come up with some discrete version of them, right? Because like curvature doesn't make sense on a polyhedral object. It's like flat and then like kinked. Shortest paths make perfect sense on a triangulated domain. Like I can ask, what is the length, like the shortest set of line segments along triangle faces that connect one point to another, right? And so you might ask, like specifically for that problem, how much structure does it have in common? Like can I come up with a formula that looks like the one that I've written on the board? And the answer is going to be like, kind of. And moreover, just like many of the things we've already seen in this course, there will be some shared structure, but not 100%. In fact, we'll see that two notions of being locally, like the shortest path between 2 points that are identical in the smooth case, as always, in the discrete case end up being different, right? This is like the same theme we keep seeing in this course, right? That there's no free lunch. Okay. So let's dive into some details. In particular, we're going to go through some material from this. Strangely, I found it in SIGGRAPH course notes. I couldn't find a research paper that details this. These guys lost out on some academia, good guy points. But indeed, if you read these course notes, they detail these problems in some nice kind of exposition and pictures and so on, which is convenient for lazy instructors like me that just hit print screen on other people's slides. Okay. So in particular, you can already kind of see, based on the schematic here, what we're going to be kind of after, right? Which is some condition to look at curves between different pairs of points on polyhedral objects, and to kind of understand the different conditions. Like what would be the analog of this projection condition we have here, right? This zero geodesic curvature condition. And how does it compare, for example, to being the shortest path, either locally or globally? Yeah? Okay, so let's get started with that. And in particular, we're going to kind of ask ourselves if we can do a very similar construction to our last lecture, where remember we studied two different versions of geodesic problem. One was like given two endpoints, find the shortest curve that connects them. That's this kind of natural one. But the other one was like find me a geodesic curve where I point my toes in a particular direction, and I want to know like what is the curve tracing out in this direction that has the property that is kind of locally the shortest path from one point in time to the next, right? And we showed that those two things are kind of related to one another. One of them is being a boundary value problem, the other being an initial value problem. Okay, so the question is, can we do the same thing on a triangle mesh? And the answer, of course, is yes, kinda. And so in order to do that on a triangle mesh, like what would be our input? We kind of have a point and a vector, and we have to decide where to go. And so in particular, we're going to divide into three cases here, which depend on the location of the point. And then our goal is to basically just infinitesimally for now, and you'll see how this will extend to an algorithm kind of easily, ask the question of how to extend our geodesic curve along the vector we're provided. Okay? So in particular, there's sort of three things that can happen. The first one, if I want a triangle, I have a vector direction. Obviously, the direction had better be in the plane of the triangle. And I want to extend my geodesic curve infinitesimally along the triangle. I want to remain as shortest path. What should I probably do? Justin, what should I do? How should I make a shortest path on a flat triangle?
Direct line.
Yeah, draw a line. right? If I'm given a point and I'm given a vector on the triangle face, then probably the best way to continue drawing a shortest path infinitesimally is to just move along that vector, right? Nothing too exciting here, right? So for at least for triangles, somehow the condition of being infinitesimally the shortest path is pretty obvious given a direction. So now you can guess where our other two, the two cases we have to worry about, right? One is going to be edges, the other is going to be vertices. Yeah? So let's deal with edges next. So essentially, when we deal with shortest paths along edges, let me see, I really struggled to draw this picture. It's going to get even worse when we talk about vertices. In high school, I took this technical drawing class that said when you want to draw lines, you look at the target of the line, not where your pen is. They had us repeat that many times, and I still can't, I can't do it. Okay, but we're given 2 points on this thing, infinitesimally maybe, like maybe this point here and that point there, and we're going to connect them. And Dustin has brilliantly told us that essentially what are our choices in the interiors of this triangle is just to draw straight lines, right? So if we think about it, what are our curves going to look like when we connect points? Well, it's going to go in a straight line into the edge, and then straight line along the other face. So in some sense, our degree of freedom here is like, where to place this point, right, in some sense. Depending on how we're thinking about it. If you're thinking about connecting these 2 points with the shortest path, then maybe that's your degree of freedom. If you're thinking of how do I extend this curve once it hits into the boundary between these 2 triangles, then maybe you think about it like the angle that it kind of comes off the other side with, right? So in other words, you run into this fold in your triangle mesh, and then you can kind of like, you're already coming over the fold, so you can't continue in a straight line. You got to go into the plane of the next triangle, but you have like a 180-degree range of directions you could choose. I think many of you can intuit where we're going with this. It's pretty natural, but there are a lot of ways to view what's going on here. First of all, I'm going to make a bold claim here, which is what is the length of this pair of line segments here? Well, one observation we can make is that it's the sum of the lengths of these 2 line segments. Yeah? So here's a fun fact. So here's an angle, right? This is the angle between the 2 triangles, like that they're flapping on, like that. Anybody know what the name of this angle is? Dihedral angle. Thank you, Anna. So let's say that I change the let's say I'm just looking at this little flap. I don't care about the rest of my mesh. Yeah? And I change the dihedral. I like make all of the triangle edges here out of iron. And all I can do, so I can't change the shape of the triangle, but I can hinge about that shared edge. As I do that, do the length of those 2 segments change? No. So here's an equivalent picture. I can take this guy and I can unfold this dihedral angle to just be planar, right? If you're wondering, these 2 triangles and these 2 triangles are the same. Yeah? So now we have our 2 points. How should I probably connect them in this planar picture to be as close as possible to one another? With a straight line. Yeah, that's absolutely right. Like that. Okay, and this is going to give us a clue as to like, okay, so the reality is we're drawing our geodesic with like an arrow like that. It runs into the boundary, and now I have this option to kind of like shoot it off into different directions in the adjacent face. And this picture is very suggestive of what direction I should choose, right? In particular, the typical condition that we write down here, I mean, there's actually 2 equivalent ones. One would be unfold and choose whatever gives you a straight line, right? Which is a totally reasonable thing. Like unfold, take this vector and just kind of displace it, right? That's kind of annoying to work with from like a high school geometry perspective. So here's an equivalent one. I'm going to erase this and clean it up a little bit. Okay. Which is as follows. Here's a triangle. Here's a second triangle, point. Let me make sure. Okay, that is a straight plane. I wanted to make sure it didn't meet the vertical line at a 90-degree angle because it kind of looked like it did. So if I look on the left-hand side of my curve and the right-hand side of my curve in this unfolded picture, how much angle is on both sides of this thing? So in other words, what is this angle? 180. Somebody else, in radians. We're going to do high school. Pi. Thank you. That's right. So in particular, the sum of this angle and that one is pi. Yeah? And similarly, what's the sum of the bottom angle and its adjacent thing? Pi. Thank you. Okay. So here's a totally reasonable way, now for your real high school geometry exercise. Let's say I take this angle here and that angle there. What's their relationship? They're the same. This is the opposite angle whatever thing. It's actually the phrase that's in the high school geometry book. Okay, so a nice condition for continuing a geodesic once it runs into an edge, because think about the algorithm we're doing, right? Like you are given a point with a little vector and a triangle face, you're just like happily walking along this mesh, you run into an edge, and now like, oh shoot, I've got to fold over to the next triangle, what direction do I choose? Well, what I can do is I can say, okay, I should choose the direction so that the angles on the next triangle resemble the angles on the one that I came from, right? Or equivalently, that there's 180 degrees on my left and 180 degrees total on my right. That make sense? Okay, and that's going to be our condition for our curve, once it passes over an edge, to be locally a geodesic, right? I think this is a completely reasonable argument. We're skipping some formulas here because I do think this is a believable picture. Right, so here's just one fun connection. What do we use for, like, remember when we had polyhedral, or, you know, whatever, just polylines as curves? What do we use as a condition? Like, how do we compute curvature of this object, roughly? Mm-hmm. That's right. I always want to call you Stephen, and you're not. Matthew. Matthew has exactly the right idea, right? Remember, we measured this thing we called the turning angle, and when essentially, you know, as the turning angle got bigger, this is some notion of like the integral of curvature in this region near this point. Notice when I unfolded, what was my turning angle when I crossed over the edge? It was 0, right? I just kept going. I didn't turn at all. So in some sense, notice that the condition I accidentally erased, that the projection, right, that there's no geodesic curvature, kind of plays out in the discrete case, right? Like in some sense, the condition that I have like 180 degrees on my left and my right is somehow quite similar to saying there's no geodesic curvature. Right? So far our picture feels pretty rosy. Life is good. But then a bad thing happens. So now there's one more case which feels like a boundary case, but actually does happen. Turns out you can like find geodesic curves that kind of spiral inward, this kind of thing. And that is, so we've done triangles, we've done, edges. I have to continue putting victory marks next to things. What case am I missing? You're always so quiet, but you realize I never ask questions that don't have like immediate answer. Louder, what am I missing? Corners. Better known as vertices, yes. Okay. So, this is where the stuff hits the fan. Unfortunately for us, geodesic curves that wham into vertices of triangle meshes can do all kinds of weird things. And this is what, like, somehow surprising and counterintuitive. And like is one of these things that's like somehow like a little depressing. Like you know, like so far our picture looks very simple. I should be able to write a little piece of code that just like scoots a curve along a surface, and then suddenly it like hits into a vertex, which can happen. And then suddenly you'll realize like, oh, it's not obvious where I should go. And let me draw a few pictures of why. And I always get these cases wrong. You can see I wrote myself pages and pages of notes because I was like nervous that I was going to get it incorrect. Oh, look at that. A spam account on Instagram wants to follow me. Okay, I really got to turn these notifications off. Right, so let's see here. So case number 3 is vertex. We're going to separate this into 3 cases, one of which we won't bother, which is if the vertex is planar. It's pretty clear what we should do. Just continue. Okay, but there's 2 other ones, which correspond to negative curvature and positive curvature. Yeah? What we're going to see, which is frustrating and confusing, is that these 2 cases lead to completely different geodesic formulas. Okay, so which one do we want to do first? Let's take a vote. We want to do negative curvature. Thank you. Positive curvature. That's strange, but okay, we'll go with positive curvature. I'm curious to hear the bias why later. I have a lot of questions. Okay, so, but the really good thing is that you guys are engaged, and that makes me happy. Okay, so let's say I have a positively curved vertex. So we have some notion of Gaussian curvature that's positive. In particular, we're going to use a notion from a couple lectures ago called angle deficit. Remember what that says? It says you can get some integrated notion of Gaussian curvature to go back to Stephen/Matthew's comment from before. And the integral of Gaussian curvature in a little cell around a vertex is roughly 2 pi minus the sum of the angles adjacent to it. Yeah? Okay, so if we're positively curved, that corresponds to like bowl-shaped stuff, right? So we're not in the saddle thing yet. Or monkey saddle? I never know why they always call it a monkey saddle in geometry books. Just call it a saddle. Anyway, so here's a positively curved vertex. Maybe. You know, I'm a geometry professor, and I'm just horrible at drawing these 3D pictures, and it's only going to get worse in this class. Okay, so there's one. So this is a vertex, got 3 triangles coming out of it. This is also called a tetrahedron. But in any event, here's what we're going to do in today's lecture, which is kind of similar to what we did for case number 2 here, is we'd like to unfold it. But can we unfold this to something planar? No, kind of by definition, like this thing is positively curved, it's not planar. But we can do, and the reason why Anna's got her eyebrows furrowed, is we can take a pair of scissors. Here's scissors, in case you were wondering. And I can cut along one of these edges and unfold. Yeah, that's perfectly kosher. Yeah? Okay. So let's do that. So when we unfold, maybe we get a set of triangles that comes out of a vertex. Blah. Like that. We can't say much about this schematic, but we can say one thing, which is we know that the angles, you know, like, so this is where we cut, right? Like this is where the scissors happen. Somehow we also grew a few edges. I'm sorry, this started as a tet, now it's got a few more, but this is schematic today. What we do know is that there's an angle deficit. Like there's going to be an open thing here where we cut, right? Because these can't add up to 2 pi. It comes up to, so in other words, remember, this is the sum. Theta I is less than 2 pi. Is an equivalent condition. Okay? All right, so let's say that I drew actually any path through this vertex. Okay? Let's draw our favorite one. So maybe, you know, it starts here, it goes up to this vertex, and it comes back down that way, whatever. You know, any path at all. So what is that path going to look like? Well, it has to start at one of these points, go through this vertex, then down another triangle. What do we notice about this picture that I just drew? We're shaking our head. What's wrong?
It doesn't look like the shortest.
Doesn't look like the shortest path on the plane. Notice that I could have done that, and I can actually take this thing and map it back. Like this is still a shortest path, right? Now this picture is a little suggestive. I happen to wham my curve into the gray area here, which is why I kind of had to take a left turn, right? And so there's a reasonable question, which is does that always happen, right? And I argue the answer is actually yes. So let me draw you the construction here, which is kind of sneaky. So let's say that I have exactly the same picture as before. We lost an edge because I'm lazy at drawing. Okay? But now I draw a path through this vertex that doesn't pass through this thing. So like a straight line like that. So it feels like that should be a shortest path, right? Like I drew it, it looks like a straight line. How many of us agree? Is this the shortest path on the triangle mesh? Locally? No. You're so confident. That's great. Tell me why. Because I asked.
It seems like you can kind of cut across the cut edge,
Mm-hmm.
and that would make it shorter.
Cool. I'm going to choose to interpret your answer as follows. I could have put, like, I have my little zipper here, but I could have cut my mesh anywhere, right? Like the edge that I chose to cut was totally arbitrary. And in order to argue that this is not the shortest path, I just have to show the existence of any path that's not the shortest path, right? Or any path that's shorter, rather, is a better way to phrase that. So here's the thing. Take a look at this thing. I could have cut it on this edge here, like that, and taken this triangle and rotated it so that, like, now I have a picture. Oh, geez, this is like that. Does this picture make sense? I took this one triangle and I rotated it like that. I should have brought props for lecture today. So in this picture, notice that now the shortest path is that, but the path that I actually drew was that. And it turns out that this construction is always possible at a curved vertex. That essentially, by choosing the right edge to cut, you can always come up with a shorter path. This is weird. What does this tell you? This tells you that there is no such thing as a locally shortest path that passes through a vertex of a triangle mesh. Now, this is mind-blowing and it's not. Like initially it feels strange because somehow the construction we made just like kind of feels reasonable. But now think about it this way. Let's say that I actually like made one of these positively curved polyhedra. I encourage you all to do this at home. I'm like looking around the room for like things with sharp edges and I'm failing. In any event, here's my challenge for you. Take a polyhedron with a positively curved sharp edge. Take a piece of string, like this cable coming out of my laptop. I'm jeopardizing our course recording. Put that piece of string right over that edge and see if you can manage to pull it tight without it slipping over the side. And I think if you think about it that way, it becomes very clear that there's never a case where a shortest path should go over that little apex. You can always kind of slip it over the side and make it a little shorter. Yeah? And that's essentially what this argument is trying to show. On the other hand, what you can do is make a path which is a slight relaxation of the condition we had above. So above, what was our condition for passing over edge? It was kind of like, if I look to my left, I have 180 degrees of angle. If I look to my right, there's 180 degrees of angle. Now, when I run into this vertex, can I enforce that constraint anymore? No, because there's not 180 degrees to work with. That's sort of the definition of curvature, right? But what I can do is ask that the angle on my left and the angle on my right are equal to one another. And then you do get a what these folks call a straightest geodesic. Right? So you don't get a shortest geodesic, like it's not locally the shortest curve, but it is the one that's sort of the straightest were you to run into that corner. Does that make sense? So there's this really weird scenario where this ODE that we wrote down for solving for shortest paths just doesn't make sense. There's no such thing as infinitesimally extending a shortest path once it runs into a positively curved vertex in a way that maintains shortest pathness. The second you cross over that vertex is no longer a shortest path for any infinitesimal amount of time. Yes?
So I guess what's drawn on the board?
What's drawn on the board? That would be the straightest path. So here, yeah, so like if you look at this corner here, on this third case on the right, what this person has done is they said, okay, well, what I can do is view my curve as essentially partitioning the angles into all the angles on its left and all the angles on its right. And it's chosen the direction coming out where those two things sum to the same thing. Yeah, so this would be a straightest curve, but not a shortest curve. I can kind of see that. It looks like if you pass through the face on the right, it would get a little shorter. Yeah, good question. Any others? I see furrowed eyebrows, and there should be, because like this is surprising. Like when you start doing this calculation, you're kind of like walking in this happy neighborhood, and suddenly it's like, oh, wait a second, that's weird. Okay. Should I take another vote? Like, should we do negative curvature now, or like this is just like a positively curved, biased classroom? We just don't do negative curvature. Yeah. Okay. So let's do the negative curvature case. I'm going to see things get even weirder. Do I want to try and fit it on this board? Yeah, sure. We can do it. Okay. So case B is k is less than 0. Okay. I'm going to give myself some space. Like that. We'll work in this little 1 foot strip here. Okay, so what is our schematic when k is negative? I always really struggle to draw negatively curved things. This is just like an annoying picture, but remember that essentially you have a lot of x-axis angle. So if I like took the little ring around my vertex and I cut once again and I started laying the triangles out in a loop, what's going to happen? I'm going to end up with looping over myself. Yeah. So like for instance, let's see if I can draw this. Here's my center vertex. Maybe I like do that. I start stacking these triangles together, and end up with a picture like this. It's getting dicey. I'm sorry, guys. There we go. Like that. I suppose the length of this edge and the length of that one really should be the same, but sorry, they're not. But notice that like if I tried to glue these two things together, it would kind of buckle. You'd end up with like a saddle-shaped object. Does that make sense? Okay. And notice that the sum of the interior angle at this vertex is obviously greater than 2 pi, right? So sum of theta I here is greater than 2 pi. So now, let's say I want to draw a shortest path between 2 points. There's something really absurd and surprising that's going to happen. In particular, let's say I choose a point here, and I choose a point on the other side, like there. No, notice there's never a case when I pass through my vertex and I go into the void. If anything, the opposite happens. I pass through a vertex and I might end up in a space that overlaps between two triangles, right? But this still unfolded to a straight line in the plane. So what did I just show? That's right. Matthew, there are multiple shortest curves that all pass through this vertex that are between these two triangles, right? And so in fact, there's an entire kind of fan worth of directions that you can choose and remain the shortest path from A to B. This is totally bizarre. So like that ODE, right, that picture that we had, no geodesic curvature, once again kind of fails because it doesn't give you enough information to determine a curve, yeah? So now there are multiple shortest paths that are all perfectly fine. Notice they don't end up at the same place. So they're shortest in the sense that like I continue being shortest when I walk along, but it doesn't say the shortest path from A to B. Okay, now you could ask the opposite question, what about straightest path? Right, so in other words, can I make the angles on my left sum to the angles on my right? And this is the case I always forget. Oh yeah. And there's still only one straightest path, right? Then you can kind of tie break between these options here, right? So in other words, the notion of being the straightest path on a curved domain is perfectly well defined. The notion of being a shortest path, even locally, is not. Yeah? So here's kind of a summary of the picture here, or to put it differently, essentially at like spherical style places, like positively curved ones, the straightest geodesic is never the shortest, right? That's what we argued. And when curvature is negative, there's multiple shortest paths now, or shortest geodesics, but only one straightest one. Yes, sir, Tim.
So a bit also, like when we say it's positively curved, we use the Gaussian curvature.
That's right. So the angle deficit is negative. Like the sum of the interior angles is less than 2 pi. Yeah. Mm-hmm.
You said that this correct case of going through a vertex would happen if you like spiral in or if you converge.
Yeah, I believe that this can happen. Like if you have a negatively curved thing, you kind of hit it askew to an edge, it'll come in. I always get this picture wrong.
But even if it's convergence, won't it like only go to the vertex like that's
Infinity?
So don't you have to care about it?
You don't have to care about. Those are famous last words in geometry. I'm trying to think if there's a case where you can somehow end up with a curve that hits, kind of funnels its way down an edge of the mesh. It would be what I would be concerned about. I'll have to think about it. You're right. It's certainly a rare case, but it is one you have to worry about. Yeah. I don't know. It's a good question, and I'll get it wrong. And my bet is if you open up these course notes, you'll find a picture. Yeah. Any other questions I can fail to answer for you? Yes.
If you like, if slightly like sand down these edges and the vertices, you would get like a smooth.
Yeah.
But in the smooth case, there is like one shortest path.
That's right. And you can pull a piece of string across the surface of a sphere.
So,
Yeah.
right. So what breaks or like,
The pointiness. Yeah. I mean, the picture that we did in our previous lecture.
just a little bit smooth, like suddenly.
Yeah, so I think what you'll find is that there's an instability, meaning that like you can get a geodesic that is really is the shortest path, but like you can remember that there's a difference between local and global shortest path, right? This is still the case if I have like a smooth cone shaped, like I take a cone and I just smooth it out, I sand it down, as you say, and then I connect 2 points. I pull this piece of string, chances are this piece of string is going to slip down the side, right? That's true even if I sand it off the top. But that's because I fixed the endpoints. I'm not solving the local problem. Right? The local problem just says infinitesimally, if I happen to run into that vertex, how do I continue? And that's a slightly different problem. Yeah. And if I smooth it down, then like at least if I take a magnifying glass at the vertex, eventually I'll have a nice smooth problem to solve and it'll be well defined. Yeah. This is definitely a weird interface between calculus and discrete math. Yeah. But these are you guys are asking the right questions because it really is a counterintuitive little set of pictures to draw here. I think this is a very surprising picture. Yeah. Yes.
How is there a whole fan of shortest paths for the follow case?
Ah. Sure. There's 2, but it turned out I could kind of unhinge this vertex and pivot it any way that I want. Right? Like, I could. Let me draw this picture. I could additionally cut this edge, and I could pivot this triangle about the vertex here. And if you think about it, any of those will provide a straight line. So there's sort of a shortest path that ranges from this vertex, this triangle here, to that triangle there. Yeah, I encourage you to do your origami and actually cut this. Actually, I think you specifically brought origami to my office the other day. Actually cut these out of paper, and you'll see. You can like draw these lines and then like take a measuring tape, and you'll see it works out. Yeah. this stuff cool? I love this stuff. This is like really surprising. There's like all kinds of weird little interfaces between smooth and discrete, and this is one of them. Yes.
Yeah, I wonder if like any of these paths could be obtained by connecting the starting and the end points
Mm-hmm.
and then trying to project them.
Ah, that's another question, right? It's the short, like, at least locally, does projected shortest path end up giving you actual shortest path? Hiding inside of one of our derivations before kind of has a clue to the answer to that. Remember, we kind of worked out the Taylor series for a geodesic curve? And one thing that you see is that indeed, like the first term of that basically looks like Euclidean distance, right? So yeah, I believe locally, one thing you can do, like if you ran into an edge, you could extend infinitesimally and then project back onto the surface, and that would give you, like certainly in the edge case, that'll give you the right direction. For the vertex one, I believe it also will, but it'll give you the straightest, not the shortest. Because there is no such thing as shortest path through a vertex. It's just, that's what we showed, right? Like you can do anything you want, it just won't give you a shortest path. Yeah. Any questions? I love this stuff. This is so much fun. Okay, so there's one footnote here. There's a funny algorithm out there that tries to kind of, it was just proposed a couple years ago, is a different sort of polyhedral method for computing these things. We're not going to go into it a whole lot of detail, but it is one method for kind of doing gradient descent on length when you're working with a polyhedral object, which is kind of cool. The way that they do it is based on an edge flip operation. So like if I have two triangles that share an edge like that, I could take that edge and erase it and kind of replace it with one that goes the other way. And essentially what you can try to do is like some edge flips to kind of facilitate your geodesic path calculation. Like maybe you want one that just cuts down like a, what do you call this, like a strip of triangles rather than like doing something totally crazy. So in any event, we're not going to cover it in this course because, well, there's a lot of other methods out there for geodesics, but this is an interesting one specifically for the boundary value problem, rather than for the sort of globally shortest path problem. That kind of extends some of the observations we have here in a clever way. So I encourage you to give this thing a read. It makes use of some pretty special data structures on meshes and so on. But it's kind of funny to see that even like, 2 years ago, people are still thinking about these problems and still making progress. Like just computing paths on a triangle mesh feels like a thing that like a high school kid that learned about Dijkstra's algorithm should be able to do. But actually, it's really not trivial at all. Also, by the way, notice that implementing the locally straightest path, like this one where anytime you run into an edge, you go over and you keep doing, like implementing it is no fun. Like it's easy to draw these pictures, but if you think about the kind of queries you'd have to do on a triangle mesh, like find me the neighboring edge, work everything in local coordinates, figure out the right angle, undo it all. These are things that are easy to draw a picture of and very annoying to get right in code. These are famously irritating pieces of code to write. Okay, so these are all locally shortest. Mary, Kate, and Ashley. That's a fail. That was weirdly distracting. So far we've talked about just locally shortest paths and like tracing a path along a single curve. Now, essentially, what we're going to spend most of the rest of today's lecture on is this sort of global version, right? Like this single source, all targets version of computing geodesic distance, right? So here we're worried with the value of the distance at every point on the surface, rather than given just 2 points specifically, give me the shortest path. Do you guys understand the distinction? Okay. Right. So basically, the question that we should all ask, because we're all computer scientists in this room, whether we're willing to admit it or not, is that we know how to compute like shortest paths on an object that's very closely related to what we're working with, right? Like in particular, we have graphs, and graphs have so many different algorithms for computing shortest path. Yeah? Give me an example of a shortest path algorithm on a graph. Dijkstra. Thank you, Matthew. How about another one? A star. Yeah, I guess. How about a third one? Bellman-Ford. Thank you, European contingent. That's right. So we have a number of different techniques, all of which can approximate these things. And a totally reasonable question you might ask is like, can I somehow like smash it with my foot hard enough and I squash this algorithm? Can I make it work for a polyhedral surface? And if you remember our past lecture, there's some obstructions to that. Namely, your shortest paths can pass through triangles, right? Like you can't just deal with the edges. Yeah? So that's the question we'd like to use. Like, can we reuse these algorithms we spent so much time learning in 6006 to solve shortest path on a surface? And the answer is going to be like, kind of. But we're going to derive more or less, I don't want to call it state of the art because that's debatable, but I would say one of the most widely used algorithms for computing geodesics on surfaces, which is something called fast marching. This goes back to the 1990s, if not earlier. It's kind of in the applied math community. And it actually applies to a wide class of algorithms, not just shortest path, but a number of different things that fit into a certain class of PDE. Okay, so here are some principles that if you think about Dijkstra algorithm, like what does it do? It kind of like, it initializes by saying, I know the distance to my source point. What's the distance to my source point? 0? Yeah, any questions? You guys are quiet. Like the distance, the shortest path to where I am right now is 0. Yeah, okay, so I start at 0, and I label my distance to everything else as infinity, right? And then what does Dijkstra algorithm do? Well, it kind of, you can think about it as kind of built from two assumptions about shortest paths. The people on YouTube just suffered from like hearing loss. So here's one, is my shortest path had to come from somewhere. Right? And the second one is that every piece of a shortest path is optimal. Namely, like if I take a shortest path and I chop it in half, then the first half of is like the shortest path from A to B. The second half is the shortest path from B to C. Right? Yeah. This is a consequence of triangle inequality. Right? So if you think of like what does Dijkstra algorithm do? It says like I have a set of vertices that I think I know the distance to, and now I'm going to find one more vertex that I'm pretty confident I can extend it to, which is essentially the closest one to that set along an edge. And it just keeps adding it. So here's what that algorithm looks like. So I have some source vertex, we'll call it V naught, and I have an array of values, D, which is the distance to all the other vertices in a graph for now, not on a surface. And I'm going to say I have the set S, which is a set of all vertices where I know the distance to that thing, right? So currently, like, in other words, where is D reliable? Does that make sense? Okay. So here's what the algorithm does. It initializes the distance to V naught to be 0. That much we all know to be true. It says the distance to everything else is infinity. This is certainly an overestimate, I think, if your graph is connected. And S is empty. Okay? So Dijkstra's algorithm, at least if you put it in abstract notation, it's very clean to look at. When you actually code it, it gets to be more annoying, right? So Dijkstra algorithm does the following. It finds the closest vertex that I haven't already decided is optimal and says, okay, now that is optimal. And then it says, okay, for all neighbors of that vertex, if I can go through that vertex across an edge to the neighbor and get a shorter distance, then I should replace my current estimate of distance with that one. So notice how this is kind of using those two observations 2 slides ago. Hopefully this algorithm is familiar. If not, we might open the Wikipedia page and give it a quick read. Okay, so it kind of schematically, well, and by the way, you can write down an inductive proof that like every iteration of this thing, S is optimal. It's certainly optimal at iteration 0. And then your argument needs to be just like if you add one additional vertex, you never accidentally give it a distance that's bigger than the distances should be. One way to argue this is that sort of the distances are always increasing as you add stuff to that set S. Okay. Sort of schematically, Dijkstra algorithm looks something like this, right? Like you just have a bunch of concentric circles that you're drawing along your graph of sort of that set S, and as the algorithm advances, you have this sort of propagating front of distances that you care about, right? And so, by the way, these sort of vertices right on the edge of like where you know distance, we often call the front. Just fun vocabulary word. Okay? There's an example in the slide. We're not going to bother. Okay. So essentially, we can think of fast marching, at least in this course. There's a whole class of algorithms called fast marching algorithms. But we're going to think of fast marching for geodesics as essentially adapting Dijkstra's algorithm to approximate geodesic distance on a polyhedral object. Okay? And it's going to be an approximation. I can't say that strongly enough. And we're going to see it in like T minus 17 seconds. Okay? But it's an effective approximation, especially for large distances, and one that most people use. In fact, I think you're hard-pressed to find a better approximation. I say, and now all my colleagues are going to cringe and yell at me. Okay, so, and again, remember the basic problem we have is that like Dijkstra algorithm on the graph edges, if this is like 2 triangles here, is going to give us that red path, and we really wanted the green one, so we need to deal with the interiors of triangles. So in fast marching, at least the version that was first proposed by, I think, Kimmel and Sethian 1,000 years ago, essentially, they make the following observation. Like, here's a picture of that advancing front, right? Like those concentric circles now on this cute gargoyle. It's funny how these different communities in geometry all kind of latch on to different 3D models. Like some people like the Stanford bunny. For some reason, the distance people like this gargoyle. And notice that, I mean, they're not concentric circles anymore, for sure, right? These are like weird curved shapes. But here's a nice thing about circles. When circles are really big, they look like lines, at least locally, right? Because like, what is the curvature of a circle of radius r? Quick review question here. 1 over r, that's right. You get an extra point to you. So in fast marching, what we do is we say, we're going to pretend like the advancing front of the distance function is just piecewise linear. It's just constructed out of little straight lines. That's obviously not true, right? Like for instance, in all the triangles adjacent to the source vertex, they're like little circles, right? For sure, because it's like little planes. But we're just going to ignore that. We're just going to call them lines. And that is the conceit of the fast marching algorithm. Does that make sense? Nods, acknowledgement, you're awake. Good, good, good. Okay, so here's what we're going to do. We're going to work through the details of that approximation on a single triangle, and then we're going to assemble it back together to make an algorithm for distances on a surface. Cool? Cool. So here's what it looks like. Really, when distance functions advance, they look like circles. But here we're not going to do that. We're just going to say, OK, we're going to pretend like it's a straight line. OK? So in particular, let's say that I do the following. I'm going to take my triangle, and I'm going to give it a convenient coordinate system, because I'm lazy. In particular, is it OK to erase this board here? Good, good, good. What time is it? Oh, we're going to do it. OK. All right, friends. So, well, if we approximate our distance function in the interior of a triangle with a linear thing, then I claim we can always write it as follows. D of x is n transpose x plus c. Now, I've used the letters n and c. But if you ignore that they're very suggestive letters, notice this is just a generic linear function, right? And the question is, what are n and c, right? That's essentially what we're going to try and figure out. And remember what the Dijkstra algorithm does. It's like trying to advance distance functions. So maybe a reasonable analogy here would be I know the distance to 2 vertices, and I'm trying to guess the distance to the third. That's going to be the problem that we're going to try and solve. Make sense? OK. So here's what we're going to do. We're going to choose a really convenient coordinate system for our triangle, which is as follows. I'm like staring at my slides to see if I want to give it away. Yeah, that's fine. Which looks like this. So in particular, we have some triangle with vertices x1, x2, and x3. Cool. And just for fun, we're going to displace our triangle by just subtracting off the origin so that x3 is equal to 0. OK? We can always do this. Like, notice if I shift a triangle, the edge lengths don't change, so it's kind of OK to do this kind of thing. OK. So in particular, we're going to say we know d1 and d2. We know the distance to vertex 1, and we know the distance to vertex 2. And our task in life is to know the distance to vertex 3. OK? Now, if we look at our distance function d, how many unknowns are there? I underline them. 2. Wrong. Why are you wrong? One of these is a vector, and one of them is a scalar, right? So actually 3, right? n is a vector, and so there's 3 numbers that we don't know. OK? And what information do we have? So first of all, we know, so x3 is the one that we don't know? Yeah. So we know d of x1, right, is equal to, so like in other words, this is maybe some number that I already had from a previous part of fast marching. We'll call it d1. And this is n transpose x1 plus c. And then similarly, we know I keep forgetting what I'm doing. d2, right, which is dx2, which in our linearized picture is n transpose x2 plus the same constant c. Yeah?
If the normal is like unit vector, this is enough, just one coordinate is correct.
Hashem anticipated exactly the next sentence of our thing here. So we have 2 pieces of information here, right? We have 2 distance values, but we actually have a third, right? In particular, like, so Hashem has got the right intuition here, which is I use the letter n because n stands for normal. We didn't actually get that yet. So far, this is just some linear thing. But remember that distances satisfy a particular partial differential equation on a surface, right? What is that PDE? Iconal equation. It's our favorite, right? It's our favorite. It's Letitia's favorite too, but she's not letting it on. Yeah. Okay, so in particular, we have a conal equation, and what does it say? It says that the norm of the gradient of d is identically equal to 1. Now, what is the gradient of d in this linearized model? I'll give you a hint. It rhymes with m. N, yeah? So, God, you guys are killing me. Okay, so we actually have 3 pieces of information. We have d1, d2, and we know the norm of n. We have 3 unknowns, namely n1 and n2 and c. So there's a hope here, right? We should have hope. So the question is, can we derive our update? The answer is, obviously, why did Justin ask these questions? He's doing it on the board, and this is frustrating. Okay, so let's actually do that. So we're all grown-ups here, so we're going to make a few definitions because we like to do linear algebra instead of like high school stuff. So in particular here, I'm going to define a vector called d, and it'll just have elements d1 and d2, like that. Okay, and we're going to make a matrix x, which we'll call x1 and x2. And just for convenience, we're going to think of x as 2 by 2. It's not, we're going to see that it actually doesn't matter, but we could rotate the triangle into the plane easily enough. Notice that like displacement and rotation are all kind of fine. They don't affect distances. But then what we're going to see is that essentially, essentially our final formula here is just going to involve like dot products between edges of the triangle. So this is just for notation. Okay, cool. So these 2 things together, what do they show us? They show us that the vector d is equal to x transpose n. I just flipped the order of the dot product here. And you want to say plus c, but that kind of doesn't parse, right? Because this is 2 by 1 and c is 1 by 1. So a standard thing to do is to say it's c times the vector of all 1s. I'll notate that with this little blackboard 1. Does everybody understand this notation here? Fantastic. Okay. And moreover, n has unit norm, so I can write n transpose n is equal to 1. Cool? Cool. All right. So what we're going to do here is we're going to solve for c. Okay. Actually, no. We're first going to solve for n, and then we're going to solve for c. So from this first expression here, or maybe we'll label this one 1, and this one 2. 1 here implies that we can solve for n, and we'll get n is equal to x minus transpose d minus c times the vector of all 1s. You see that? So I subtracted this from both sides and then multiplied by the inverse of that guy. Everybody with me? Okay. Right, so here's our formula for n. This is great because it says if we know c, which is a scalar, we get the 2 elements of n. So we're doing pretty good here. We kind of eliminated a thing. Okay? So now we got to find c, and that's going to be annoying. So let's do it. All right, team. So it would be great is if we could use the other 6 boards in this room. But I'm over it. It's fine. Okay. So any ideas? How are we going to find c? Like, what's going to be our strategy? What information haven't we used yet? Yeah, I numbered off 2 equations. One of them is 1 and one's 2. We use 1. We're probably going to use 2. Yeah. So in particular, let's write this down, and in excruciatingly painful fashion. Okay. So first of all, there's equation 2. By the reflexive property of the equal sign, I can change the order. Okay. So let's plug in our formula for n transpose n. So we're going to get d minus c times the vector of all 1s transpose times x inverse transpose times d minus c times the vector of all 1s. You believe me? You should check closely. We have lots of evidence in this class that I do calculations wrong. Okay. So for my next trick, we're going to expand this giant product just to make this a little uglier, okay? So in particular, what are we going to get? So we let's start with the let's start from actually the right and work our way to the left. So we have C times 1 transpose times X inverse transpose of C. Okay? So this is going to be the following: X transpose X inverse. You guys see how I got that coefficient of C squared? So notice C squared is going to be this term, that term, that term, right? So we see there's 2 of the vector of all 1s. And this is equivalent to X inverse transpose. I just parenthesized it. Cool? Notice, by the way, to go back to an earlier question, like I was lazy and I displaced my whole problem to the origin and then rotated it to be in the plane. But notice that really what this matrix is just the dot products pairwise between the edges of my triangle. I didn't really have to do that. Yeah, this is just lazy. Okay, so let's work out the coefficient of C next. So we have C 1 transpose X transpose X inverse D. Cool? Cool. So in other words, and we get 2 of those, right? Because there's one because of FOIL from high school algebra. Yeah, so this is minus 2 1 transpose X transpose X inverse D. All that times C. Okay? You get quiet every time I do a boring calculation. It's no fun for me. I want really responsive. Okay, and now part C, or the third piece here, is the constant term, which is D transpose this thing, D. Yeah? So we have D transpose X inverse D. Okay? Now, we're going to define 3 constants. Because like, what do we know and what do we not know in this expression? We don't know C, and we do know X and D. We actually know everything else. The only thing we don't know is C. So this feels complicated, but we can actually define a bunch of constants. Let's do that. Let's call this thing, oh boy, every year I regret my choice of notation and I don't fix it. Let's call this A bar, because I'm going to have a C in a second and I don't want to conflict. Okay, we'll call this B bar. We'll call this C bar. These are constants, right? These are things I know about my triangle. Like, that's perfectly kosher. I can write a piece of code that computes these things and never look at them again. So when I do that, what do I get? I get A bar C squared plus B bar C plus. Does that look familiar? Remember what my unknown is? What's my unknown? C. How am I going to solve for C? Quadratic formula. Fantastic. Who wants to help me out? C equals negative B bar plus or minus the square root
of B bar squared.
B bar squared minus, oh, sorry.
Minus 4 times A bar times C bar.
Think for a second. Look at the left-hand side of our equation. It's a 1. See what I did there? So C bar minus 1. All that divided by 2A bar. Round of applause for Matthew here. Yeah. What was that?
You're solving for C. Why is it a C there?
It's a C bar. Totally different.
Oh, okay.
You can see every year I get 2/3 through this thing and I regret my choice of letters because I want it to look like the quadratic equation. I should probably call that like X and then X something else, but then I have to revise my slides and the course notes is a whole thing. So instead we just make the same stupid mistake in lecture every time. Okay, or we just call you guys grown-ups and give them different labels and you can probably still apply the quadratic formula. Okay, so we have a formula for C. This is fantastic. There's only there's an obvious problem here though. There's 2 of them. Yeah, we got a plus or a minus here. And the question is, what the heck is wrong with that? Like what's going on here? Okay, so far we've done this calculation, which hopefully agrees with what's in my notes. It does. And now, right, we can solve for C, and we're almost there, but we have 2 options for D. And the question is, like, how do we choose among those 2? And it turns out there's actually a really intuitive picture of what's going on in these 2 roots. So remember, you have this advancing planar front of distances, right? And so there's like this kind of line that's moving along the plane and is bumping into one vertex at a time. Yeah? And so in general, think about the ambiguity of this expression here, that n transpose n is equal to 1, right? There's always the same problem with normal vectors is that we don't know their orientation. We only know, you know their unit vector, but we can flip it by -1 and still get a normal vector. It's just minus that thing, right? And so in essence, if you think about it, this difference in sign is exactly like choosing the sign of n. That's why this thing is ambiguous, okay? And so pictorially, here's what's going on. I can think of placing n at x3. Remember, that's the place where I don't have the distance. And you can actually sort of construct an advancing wavefront that hits x1 and x2 with the same distances, but travels along n in the first case where I think of hitting x3 before the other two, and the second one where I think of hitting x3 after the other two. Now remember what Dijkstra algorithm does, right? It's trying to make the front bigger and bigger and bigger. So by that sort of conceit, which of these two routes should I probably choose? The larger one, right? Because we already know the distance to x1 and x2, and so like if you think of the way a Dijkstra algorithm works, you expect the distance to x3 to be larger, right? Because you're advancing your front. So in other words, we just take that plus or minus, get rid of the minus. Okay? Now, it turns out that like this picture is very rosy. Like this is what you hope happens, and this is what happens for like well-behaved triangles that only drive on Sundays and have acute interior angles and all that kind of stuff. For obtuse triangles, you can end up in a really frustrating scenario where, oh, oops, right. So this is the good picture, right? So this is the one where you have the front that hits x1, x2, and then x3, which is what you hope for. You can end up in the following situation where the normal that's implied by the calculation you did, neither of the two normal directions is in the plane of the triangle, right? Notice that's like kind of what's going on here. And in that case, what'll happen is you might do like x1, x3, x2, or something like that, which is invalid. This is easy to detect, right? You can look at that normal and just see, is it inside of this triangle or not? And if it's not, then it turns out there's an entire list of heuristics people use to break the tie. So essentially, in that case, the planar approximation just is wrong. Like it just doesn't, it's not consistent with Dijkstra algorithm. And so there's some deep reasons why. If you think about the front of distances that should really propagate over a triangle mesh, it's actually composed of these little tiny circular wavefronts, and every time it hits a vertex, that circle like kind of cuts in half. And so it gets very complicated. Like it's not enough to just know these two distances. You kind of have to like divide the edge up into all those little wavefronts if you want to do this correctly. And this is kind of what happens. Like your approximation starts to break down. So in practice, what people do is they detect this case. Like maybe you compute x3 using this formula, and you find, oh shoot, like the distance to x3 is smaller than the two I have, and that's invalid. Typically, they will throw it away and then replace it with the distance you get by forcing yourself to travel along one of the edges. Is that correct? No, this is an approximation, but it's a pretty good approximation. If you go, there's this textbook by Bronstein et al. They call it Numerical Geometry of Non-Rigid Shapes. It has a really creepy cover with like a 3D face getting pulled off of another 3D face. I don't know why Michael did that. This is the same Michael Bronstein that many of you guys probably recognize from now modern graph neural networks. Before that, he was doing this kind of stuff. If you take a look there, they have a whole list of different heuristics you can use to fix this case. There's some other things you could do, like maybe cut this triangle in half and advance twice or something like that. And there's a whole literature in the 90s of people that had all kinds of like clever heuristics for improving, essentially when this planar wavefront breaks down. One thing that I forget if I put in your homework this year or not, actually I have the freedom to do tonight if I feel like it, is you can actually check this condition, like that there's like a little formula for just checking whether or not the distances are valid. So it's actually easy to detect in practice. There's a lot of pictures of this in the slides. Okay, so like some reasonable fixes here might be to just like do graph-based Dijkstra update when the planar one fails. Or there's some other ones. So for example, there's a pretty famous one from Kimmel and Sethi in 1998 where they kind of show that like typically this problem happens when you have badly shaped triangles, like big obtuse stuff. So maybe you kind of cut it in half, put a virtual vertex in between, and do this update 2 times or something like that. Yeah, so there's all kinds of tricks people use. Okay. So that basically is everything we're going to need for the fast marching algorithm. Instead of doing Dijkstra where you add one edge at a time, we're going to add kind of one triangle to our advancing wavefront at a time. And that's basically it. Right? So the differences are going to be a slightly new update step, and that like when we look at the local neighborhood of the thing we just added to the set S, rather than looking just adjacent edges, you look at adjacent triangles as well. Yeah. Okay. Notice, by the way, that you can view that algorithm as basically a solver for the O'Connell equation under the one assumption, which is completely false, that we made, which is that the wavefront is planar, right? And so from that perspective, you could take a whole class of PDEs. So notice that, like, I'm looking for the O'Connell equation. It's not actually written down anywhere. Oh, yeah, there it is. That is a partial differential equation to define D, right? And basically, based on that, it gave us some update formula for how to move our planar wavefront forward. I could have cooked up some other partial equation I want to solve, right? Like maybe grad of D plus some constant dot product with the grad of D is equal to 7, right? And I could have followed exactly this derivation to get some other update for x3. And so in fact, this is just one example of a problem you can solve with fast marching. If you want to solve others, you have to be a little bit careful to make sure that it still has this sort of distance-looking structure to it, right? Like the other assumption we needed is that you have this advancing front of values, yeah? But anyway, this is just to suggest that actually this is the tip of a big iceberg. There's this entire class of differential equations called, Hamilton-Jacobi equation, I believe, that all kind of fall into this form. And this is the generic kind of strategy for deriving an update formula. Okay. Now this, I should warn you, is still an approximation, right? Like as I try to argue to you guys, the wavefront is not actually a straight line, even on a triangle mesh. It should be like circles. and so somehow this update formula is just a little bit wrong. Just to test your intuition a little bit, where do you expect these distances to be the most inaccurate? Yeah. Close to the source point. Yeah. Why is that? Yeah, it's the most not aligned. That's right. To put it differently, like there's a large amount of curvature in the wavefront close to the source point, right? So this approximation is particularly bad. And indeed, when you look at the distances you get, like if you plot accuracy as a function of distance, which is a weird thing to say because you're computing distance, you'll see that it gets better as you get farther away. Yeah. Any questions about that? I see a question. Yeah.
Is there a non-approximate algorithm for this?
Yes, there is. Is there an algorithm that doesn't compute distances approximately? Yes, and we'll come back to that in a few minutes. We're not going to cover it in detail because I hate it. I'm your instructor. I get to do that. Yeah.
So, could you just explain again how exactly we create the plots?
Yeah. So if we go back to Dijkstra algorithm, right? Where it is, here, right? So hopefully you believe this algorithm. So essentially, fast marching does exactly the same thing. So you still have a set of vertices that you kind of believe, and now you choose the closest vertex that you haven't locked in yet. You lock it in, and now the only thing that changes is this formula on the bottom. So here, what do? You look at all the edges that are adjacent to your vertex, and you update the paths along those edges. Instead, you look at all the vertices adjacent to vertex V, or sorry, you look at all the triangles adjacent to vertex V, and you apply this update formula to approximate new distances nearby. It's the only difference. Yeah. Mm-hmm.
Last lecture we had like a Dijkstra won't converge as we asked you to refine the mesh.
Yeah.
Does this one?
Yes. Yeah. This guy does converge. I believe technically you need you can't have wildly terrible triangles. So in particular, like, when you ask about convergence, like when you refine a triangle mesh, does this thing give you the actual distance value? There are a lot of ways to refine things. And like for instance, if you had a triangle that's like this, and you subdivided it in a 1-3 fashion, so you put a vertex in the center, you connect it to the corners, notice that you still have giant slivery triangles. And so somehow this kind of thing can obscure shortest paths, obviously, because they tend to pass through edges. So I think you need to kind of exclude this case. So I think if you look at convergence theory for this stuff, essentially, usually the way they phrase it is in terms of interior angles of triangles. Yeah. That's a good question, though. Yeah, these are, I believe convergence theory for this stuff is not great because, and when I say not great, I mean like just the theoretical, like it is well known to do well, empirically speaking. But the theory here is really hard because you're solving an extremely nonlinear PDE, which is this O'Connell equation. That square is really a problem. Yeah. Any other question?
So we have this like this defined on the vertices.
So if you have the distance on 2 vertices of a triangle and you want to impute the distance on the third, right? And essentially what we worked out is a formula for doing that, yeah? So you have a set of vertices whose distance you kind of trust, and now you look at all the triangles adjacent to that set, and that gives you an update for all the vertices adjacent to the vertices whose distances you trust.
No, what I mean is that, like, for instance, if you have a point, like a starting point inside of a triangle,
Mm-hmm.
we need to get the front estimated, like, inside of the triangle.
Ah, yeah.
This number is the equal to.
That's right. So here there is there is an assumption, which is your starting point is a vertex of your mesh. If you wanted to, you could take a single triangle and divide it in 3 to put your starting vertex anywhere. And notice that I guess actually, Trevor, I don't know if that's the way I would do it. I mean, I guess you do, if you had an interior vertex, you could compute the distance to the 3 vertices of that triangle and then start this algorithm from there. I think that would work. I'd have to think about it. It's a good question, yeah. But I think lazy programmers would just subdivide that one triangle and then call their fast marching code. And that'll probably be the same, because typically you initialize fast marching with just the edges out of the first vertex, because you know, that's like the one set of distances you know, right? It's like the edges out of the source vertex are truly the shortest path. Yeah. Kind of by definition, right? They're straight lines. Anyway, there are a lot of different implementations. One thing to know about fast marching is like it's not just one algorithm, it's a whole class, and there are many different variations out there. If you download people's code, like they often don't agree 100%. Yeah. And there are a lot of little heuristics. Okay, right, so you guys are all uncomfortable with the approximation of this thing, and that's good because it is uncomfortable. And you kind of have to convince yourself you haven't done anything totally unkosher. Sorry, I'm trying to find where I am. There is a reasonable question that you guys haven't yet asked, but I'm sure given another minute or two you would, which is like, okay, so there's exact geodesic distance on one side of the spectrum. There's graph shortest path on the other. Now we've kind of moved in a little bit. We have fast marching, seems to be better. Is there something else in this space in between? And the answer is yes. I mean, there's this huge literature on computing geodesic distances on polyhedral surfaces. Yet somehow, actually, fast marching is still the one most people just end up using at the end of the day, if not one or two other alternatives I'll mention that have nice code available. One thing folks did, like for example, all the way back in 2002, this is the older literature as geometry processing goes. You could say, okay, well maybe the planar wavefront approximation is not so good. I can do slightly better by having a circular wavefront, right? And notice that like somehow that's just going to lead to a different update formula. And it's also still not correct. The wavefronts for geodesic distance on polyhedral surfaces, they're also not circular. But you know, you can go through exactly this derivation and just use a different formula for d where you started with. So for instance, like d of x is equal to maybe the distance from x to some x naught that you don't know, or something like that. And so like that's what these folks do. What they find, kind of unsurprisingly, is that the quality of their distances improves close to the source point, because that's where it really does look like a circle. And then away from the source point, they run into numerical issues because the radius of their circle is so huge. Yeah. So you know, there's no winning here. Yeah.
Why can't you just do both? Start up with the...
You absolutely can. Then the question you have to ask is like when? How do you transition? Where do you detect that? But there, yeah. Or you could approximate with the...
results, and you know when they're like different maps are maybe.
You could compare the two and know when they're. You can know when they're close to each other. Can you know if they're close to ground truth? I don't think so. Yeah. Yeah. So there's a lot of reasonable questions here. There are also some modifications of fast marching. It turns out on a grid, fast marching is still an interesting algorithm because it's somehow shortest path. It's solving problems like shortest path inside of a polygon, like that kind of thing. So for instance, you can use it to solve mazes. Interestingly, in the 1990s and early 2000s, there's a lot of research in like how might one implement fast marching on a graphics card, like these kinds of things. The answer is roughly poorly. But there are methods out there that try to adapt it specifically for grids, and there's some really interesting techniques people use to like use it to solve mazes and that kind of thing. There are other alternatives to this method that are growing in popularity. There's one that I should mention because it's particularly popular in graphics community. We're going to defer discussion of the algorithm until we have the ingredients we need to do it. In my mind, a couple years ago, in your mind, like when you were in middle school, there was an algorithm that came out from Crane, Clarice Weichedel, I don't know, I don't speak German, and Max Wardetsky. They called the heat method for computing geodesics. This is based on diffusion. So essentially, in some sense, they're replacing a conal equation, which is a nonlinear PDE, with a linear one. and they kind of show that the log of the heat kernel on a surface looks like distance for small amounts of diffusion.
Here's what I found.
Gosh, this watch is the worst. Heat kernel, I got it right that time. We're going to defer discussion of this algorithm until you know what a heat kernel is. So we're gonna punt on this one. But this is a popular algorithm in graphics. It turns out asymptotically, it actually has the same runtime as fast marching, roughly. But it can leverage these fast linear, sparse linear solvers that are easy to work with in code, like you already have on your homework. So it's quite popular, especially if you're feeling lazy about implementation. Like it's just like all the building blocks are kind of already there in your geometry code. Right. And then, by the way, one just small addendum. Notice that we've now been computing distance functions, but I didn't actually have to like get the shortest path from A to B given that function. But that's actually quite easy to do, and you can do it basically with, in some sense, gradient descent, right? So like if you're in some interior point of a triangle, and you want the shortest path back to the source point after you've run fast marching, what do? Well, you have this direction n interior to every triangle, which is telling you the direction the wavefront is kind of propagating. So you can just move along that backward until you get to the source point. I'll let you guys think about that later. So to go back to Anna's question, notice that we have 4 minutes left in class, and that's because I do not plan to actually derive this technique. There is an algorithm for computing exact geodesic distances on polyhedral surfaces. Typically, we call this MMP algorithm, which stands for Mitchell, Mount, and Papadimitriou. If you recognize any of these names, you might, because they're famous computer science theorists. And the reason is this algorithm is really hard to implement. It's a huge pain in the tuchus. It's still polynomial time, but it's no fun. The basic observation here, like if you wanted to draw a little schematic of what this looks like, it's something like this. If I have a source point, and I kind of trace an actual shortest geodesic along the surface, notice that there's like this little window where I could have unrolled a sequence of triangles, and it looks like a straight line. And if you kind of look at this little pair of intersections here, the wavefront really is a circle in that little window. Do you see that? But the annoying thing is that that window segments an edge, right? And so like, it's not the case that my wavefront is a circle. It's not a line. It's not any of these things. It's like this weird piecewise combination of little circular chunks, right? And so what the MMP algorithm has to do is it's kind of like Dijkstra algorithm, but when it advances the wavefront outward, you have to do so in a way where you cut edges into pieces, right? So you can say, oh, okay, only in this segment can I actually convince myself that the shortest path kind of continues along this ray, something like that. But then you have to ask this question, which is how do I know that every edge gets cut into a finite number of pieces, and how do I bound to make sure that every edge doesn't get cut into an exponential number of pieces, right? And so that's where the hard math is hiding in that paper. That's not something we're going to cover here, but I encourage you to read it and just feel the pain that we all do when we try to read that paper. I see your hand. I'll get there in a second. There are implementations out there, but notice, so MMP was 1987. That's the year I was born. Fun fact. This paper was, I think, arguably the first practical implementation of MMP. Notice it's dated 2005. This is not like an obvious thing to implement. But conveniently, they shared their code online, so you don't have to. Anna, any question?
Is this kind of like it's basically flattening out the mesh?
Yeah, I guess you can think of it that way. Yeah, they use different language. They talk about these sort of windows. Like they take every edge and segment it. So like basically, if you think of like tracing your shortest path backward along the surface, you can think of these little windows as like all having the same path back to the source, topologically speaking. So like conceptually it's not hard, but numerically it's really hard, and theoretically it's even worse to show that, like, because you have to bound the number of cuts that you make, right? Like even convince yourself this algorithm terminates in finite time. Like for all you know, somehow the windows just get smaller and smaller and smaller and keep wrapping around the surface or something. Yeah, it's wild. It's cool. I love this stuff. Okay, some other terms that are just worth noting. We're not going to spend any time in this class. There's a particular object called the cut locus, which is kind of where the geodesics cease to be minimizing. Actually finding the cut locus is itself kind of a fun computational problem. You can kind of sort of do it using fast marching, but as you can imagine, it ends up kind of jagged. A different problem people study is approximating smooth versions of geodesic functions. So geodesic distances are not smooth. They're not even differentiable. Like if you think about that cut locus, like you have two different shortest paths that meet up. There's no reason why when they meet up, so like something global happened, right? that there should be differentiability at that point. Typically isn't. But for some applications, you want something that looks like distance but also is smooth. And lots of people have studied different ways to do it. For instance, there's this fun paper in 2010 called Fuzzy Geodesics. I encourage you to give it a read. It's just a simple formula for one way to kind of get around that problem. And then these days, of course, our data is noisy, and half the time we have some weird, gross triangle soup, and like we scanned it, and we're missing a big chunk of it, and we still want to compute distances. These are reasonable questions to ask, but of course, all of these algorithms strongly depend on being able to walk along a mesh. So you need an entire other class of things to solve those kinds of things. For instance, Kampen and Cobalt back in 2011 proposed one of the early algorithms for like kind of building a scaffold around a mesh to kind of help you do this geodesic computation. Since then, I'm guessing the neural network folks have all kinds of new solutions to these problems. They change all the time. And then finally, all pair shortest path to my knowledge is largely unsolved, as is like geodesic Voronoi kind of Delaunay stuff. Just one final note. Remember I mentioned that like you have to be so careful approximating shortest paths on graphs with shortest paths on manifolds. This is like kind of a problem on surfaces, but I'd argue we just addressed it for the whole lecture today. But where it's really a problem is in like high dimensional stuff. Like you have a big data set and some high dimension that you think forms a manifold and you'd like to compute paths, then you don't have all this nice polyhedral structure we just wrote down. And you have to be careful. So for instance, this research paper points out that like k-nearest neighbor graphs do not give a suitable shortest path on data manifold, which is surprising and annoying. So I encourage you to read this paper. I love the way they phrased it. They say, at least for unweighted KNN graphs, that the shortest path on this converges to something unpleasant, which is a nice way to put it. But there's still some theoretical progress here, and this changes all the time. I'm rushing, but maybe we'll skip that. Yeah, and there's some, I've included some pointers in the slide to some like modern methods for computing distances and so on in the machine learning context, where you just have like little data points sampled from a manifold. You don't have this nice polyhedral structure. All right, folks, but we're out of time for today, so we'll call it. Hopefully you get the basic idea of the fast marching algorithm and some of the challenges in computing geodesic distances on surfaces. And with that, I hope you have a lovely weekend, and I will see you on Tuesday. What day is today? Yeah, Tuesday. Okay.